So we want to prove the theorem of Stone now in the unbounded case or the strongly continuous case for our groups, and the idea is more or less the same as in the case for the bounded situation. We only have now not to work with uniform estimates, but we have to apply everything to vectors. And in particular, we now expect that our generator is not defined everywhere, so we also have to take a domain for the generator, and of course this domain will be clearly the vectors for which the limit which we have to take exists. Yeah, let me start this. So I mean, we define now really things as we would like to have it. So our operator, the generator, should be 1 over I times the derivative of our group. So it should be dt of ut at t equal to 0. And of course, we don't expect that this is defined everywhere. So the domain of our operator will be exactly the vectors for which this limit here exists. So we are setting d of t as those x in the Hilbert space for which this limit t going to 0 of this limit, the difference quotient for the derivative applied to the vector x. So this is ut applied to x minus u0 applied to x. u0 is the identity. So here I just have x dividing this by t, and this limit should exist as a limit in my Hilbert space, of course. So those guys. And of course, if this exists, then this limit here is what I'm going to call tx or itx then. So this here is then by definition I times tx for those guys in the domain for which this limit exists, for x in the domain. Yeah, but of course we still have somehow the main problem as in the bounded case, namely how can we be sure that this limit exists? And now we even have to see that this limit, sometimes it exists, sometimes it doesn't. But the crucial point we have to see is it exists in sufficiently many cases. So namely, an unbounded operator must have a dense domain. So now the main problem which we really have is to see that this exists for x which are dense in my Hilbert space. So the main problem in this context is we have to see that d of t is dense in H. So again, we have to find a way of controlling when does this limit exist. And for this, we're using the same idea as before. So we are not trying to attack this limit directly, but we're doing it by rewriting things in a form as we had it before, which in particular invoked this operator xt. So we define this as before. So as before, we define this operator xt. This was 1 over t times the integral from 0 to t u tau d tau. And we rewrote things in this. Yeah, and then we have now to see what properties do we have before the ut were norm continuous, which meant this xt is also norm continuous and going to 1 if t goes to 0. Now we still have that it goes to 1, but only in the same way as ut goes to 1, namely in this pointwise sense. So what we have now is not that an operator norm xt or xs, let's say, goes to the identity, but only if I'm applying it to vectors. So then what we have is that, let me call here xs for s going to infinity. If I apply it to a vector, then it goes to the x0, which is, I mean x0 is not really defined here, but of course I'm saying it has a limit. So namely xs goes to the identity in the sense that this here goes to 0 if s goes to 0. Yeah. Okay, and then the crucial property, the relation from which we more or less proved everything, was this relation which connected some quotients for t and s. So we chose 2 times, and then we had an equation, and this equation is still true. So this only used the semigroup property. So we still have this property, which I called star before. So we still have this. So maybe let me write it down. So what was this? So it was that ut minus 1 divided by t times xs. This is the same as us minus 1 divided by s times xt. So we have this if s and t are small enough. Yeah. Okay. And so, but now, before we could now work on this equation and taking the limit t going to infinity, because we knew that this goes to 1. Now we don't know this. What we only know is what happens if we apply these two vectors. So let us apply this equation to some vector. So namely, let's say I'm taking here vector y. I'm applying this to a vector y, and I can do this for any y. And now I know what happens with this guy if s goes to 0, namely this just goes to y. This converges to y if s goes to 0. And then again I can now say, okay, so let us take this equation, fix t, and send s to 0, and then this side has a limit, so this side also must have a limit, and this limit must be the limit of this, but now applied to a vector, but this vector is now this guy. And the t is not changing, the t is fixed. So I'm applying this side here to a vector, which let's say I call this here x. So, and now if I send s to 0 for the fixed t, then I'm getting on this side ut minus 1 divided by t times y. So this goes to y. If s goes to 0, that this must be the limit of this applied to this vector. And in particular, this shows me that this limit exists, because the limit on the left-hand side exists, so it must also exist on the right-hand side. So this means I have here the limit us, but now applied to this vector, so to this vector x, minus 1 applied to this vector, so minus x divided by s. And you see, this is now exactly the limit which we need for our domain. The vectors in the domain of my operator t are those for which this limit here exists. But now you see we have here situations that this limit exists, and what do I have here? I have here an x which is somehow special because it is of the form xty. The y I can choose arbitrarily, but the xt of course is given, so I have no freedom. So I only have here an x which is of the form xty. But for all such x's, I know that this limit exists. So this means all those guys are at least in my domain. And this tells me that the domain is quite big. So what we see from this, first of all, is that vectors which are of the form xt of y, they are in the domain of my operator t for all y's, for the y's which are arbitrary. But of course the t is here bigger than 0. And maybe, not even small enough, because I'm not going to invert here anything. Up to this point, I don't have to bother whether xt is invertible or not. And of course, invertibility is not so clear anymore. So in this approach here, better I'm not inverting the xt. But you see, I don't need it here, because I can check this equation here without inverting anything. And then I'm just taking limits. So this tells me that I have here found many vectors of this form, which are in a domain. And now the question is, of course, are those vectors really dense? And because xt goes pointwise to the identity, you see that any y, essentially I can approximate by xty if t goes to 0. So this means actually the vectors of this form, they are really dense. So since we can approximate y by xt of y, because this goes to 0. If t goes to 0, so this tells us that the collection of all xty for y in h and t is bigger than 0, this is really dense in h. And this here is a subset of the domain. Those guys are in the domain, so this means the domain is really dense. Okay, so this was a good step, and really this was somehow again how we could control the derivative. So how to see that for sufficiently many x's we really have a derivative of this guy here. And again, this was by using this relation here, which was essentially looking on the integration over the u's. Again, we're controlling the derivative by looking on the integral. So it's a very very nice approach. Good. So we have here a densely defined operator, and of course the main statement about this operator is that it is self-adjoint, and not just symmetric but self-adjoint. So that's now the crucial thing which we still should see. So now we have to show, and self-adjoint really with respect to this domain. So we have really fixed the domain of T, which means the adjoint comes with its domain, and then we have to see that the two domains are the same, and of course that the action of T and T star on them is also the same. So now we have to show that T is self-adjoint. And so what does this mean? So recall, how did we define in particular the domain of our T star? So we consider, let's say we consider an element in the domain of T star, and the domain, what are the guys which are in the domain of T star? So those are the y's for which there exists a vector. So this means there is an element set in my Hilbert space such that for all x in the domain of T, I can write the inner product Txy also by essentially bringing this on the other side, and then I have x comma something, and this something is now the set, so there must be a something on this side. So I must be able to write this as x comma set, and of course this set will then be the T star of y. But essentially what you have to see, if you want that y is in the domain of T star, you have that this equation, that you find a set such that this side is always, whenever this makes sense, so this means for all x in the domain of T, that it is always equal to x inner product with z. And then, so that's exactly what tells you that y is in the domain, and it also tells you what the T star of y should be, namely it's exactly this set here. And so we have to see what this now means here, in our setting. Good. Okay. So let us try to control this. And of course, what we would like to see is that this condition on the y is exactly the same as the condition which we have for the x's, for the elements in the domain, namely that this limit exists, and that of course the set is this limit applied to the y. So it's again a kind of, in principle, it's a kind of partial integration. We have to bring our u, or the limit, from one side to the other side and see that it does the same there. But also controlling the domains, so that we have chosen our domain here as big enough. Yeah, good. So what we have to see. So let us start on this side here and see what it tells us about the y. So I mean, it tells us in the end, we know something about the y, namely that there must be a set here. And so let us see how we can use this. So maybe this side here, let me start from this. So this is the Txy. I want to work with this, and for this, of course, so I'm writing down what the T does on the x. X is in the domain, so we know that the corresponding limit exists. So this is 1 over I times the limit t going to 0 of utx minus x divided by t. That's tx, and we take the inner product with y. Yeah, and now we write this out. So first this 1 over I comes out as a 1 over I, but with a complex conjugate, because I'm antilinear in the first component. So it actually comes out as an I. Then I have the 1 over t. Let me also take this out. And then I have here essentially two terms. And of course I have the limit, and the limit applies to t. So maybe I should write first the limit and then the t. Limit t goes to 0, 1 over t. And then I have here the utx inner product with y, utx with y, and I'm subtracting the x, y, inner product between x and y. So I just have written it out. And now, of course, I want to bring things on the other side. I mean, I have to move from one side, the inner product, to the other. And so here, of course, we are moving over the ut. This appears on the other side as the ut star of y. But we know the ut is unitary and it satisfies this semigroup property. So this means that the ut star is just the u of minus t. So this here I can write as x comma u minus t of y. So if I'm bringing the u on the other side, it will not appear as the ut, but it will appear as the u minus t. Okay, and this of course goes nicely with the signs which we have there. Yeah, but let's see. So what do I have here? How can I write it? So now you see I taking here the limit of here this difference is like the difference quotient, but not at time t, or I'm not at the point 0, but the increment is now not t but minus t, so I better should also have a minus t here, which I compensate by also putting a minus here. So I'm writing this as a minus I, still have the limit here, t going to 0, but here I'm writing 1 over minus t. So this minus and this minus goes away, so I have done nothing. But this minus t fits better with this minus t here, so I have here x comma u minus t of y minus y. So this is x, u minus ty, this is this quantity, and then I'm subtracting x comma y. Yeah, and now of course let me bring in all the guys here to the second argument. So I have here the inner product of x. The minus I, let me see, the minus I here appears in the second argument as a minus I, which I can also write as 1 over I. So I'm writing this as 1 over I. Then I have the limit. I also move the limit in. Limit t going to 0. And I have here u minus t y minus y divided by minus t. And this is now the derivative of ut at the point 0. But okay, instead of t, I'm going with minus t. But t goes to 0, so this is the same. And here is the inner product. Yeah, okay, so this is, if I start here, and I'm just rewriting it, and I get something which involves a limit on this side. And I mean here I have a y, so for this y, a priori, I don't know whether this limit exists, but my condition that y is the domain of t star tells me that this side here is actually the same as x comma z for all x in the domain of t. And this is a dense domain, so this tells me that this limit here must exist, namely it must be equal to this. So if, so I'm taking this side, and this side is a priori this limit here. I don't know whether it exists, but then I also know it must be this form, so this tells me that this limit here exists and it is equal to z. But this, the existence of the limit, tells me that y is in the domain of t, and this z here is t star applied to y, and this is now exactly the same as the action of t applied to y. So let me write this down, maybe as the final conclusion of this proof. So this was the main step. So we have now done all the work. I'm just writing it down, and then there are a few more details to check, which I'm not going to do, because this was the main argument, which again showed how we can work with determining the adjoint of an operator and really deciding whether it's self-adjoint or not. We have to control the domain, but we can really do this if we are doing it in a nice and correct way. Yeah, so the implication of this, or what we have shown, is that for this y, this limit t going to 0 of ut y minus y divided by t, Now I just, instead of minus t, I'm writing t. For the limit, this doesn't make a difference. This exists, and actually this limit is equal to minus I t star applied to y. Because this set, okay, maybe I have forgotten. No, did I? No, this set is t star of y. But this set is this limit up to this factor 1 over I. So this appears here explicitly. And maybe not with a minus sign. Good, yeah, but this tells me, the existence of the limit tells me that y is in the domain of t, and that this here tells me, I mean, this limit here is t applied to y, but it is also t star applied to y. So this tells me that t star of y is the same as t of y. Yeah, and so from this we see that the domain of t star is the same as the domain of t, and the action of t and t star agrees on the domain. And this just, of course, means that t is equal to t star. T is really a self-adjoint operator. Yeah, okay, and then, so we really have now, yeah, proven, shown, calculated that we have a generator, a densely defined operator, which is self-adjoint, and then, of course, it remains to show that the relation between ut and this t is exactly this. But this is now, again, just easy checking. So this is something which I'm not going to do here. Then easy to show that really the relation between ut and the generator is given by e to the I t times this generator. And this is the end of the proof of this theorem of Stone.